everyone. Welcome again to another video lecture on the chapter Solutions. In this video, we shall talk about the abnormal molecular masses and Van Hoff factor. Now, in the previous lessons, we have learned and derived the relations for the various colligative properties. However, these relations are applicable to the solutions of non-electrolytes only, which do not undergo any dissociation or association in the solution. Now, dissociation leads to an increase in the number of solute particles in the solution, resulting in an increase in the value of colligative property. Also, since colligative property is inversely proportional to the molecular mass of the solute in the solution, the molecular mass of each of the substances as calculated from the colligative property will be less than its normal value. For example, in the case of aqueous solutions of electrolytes like KCl, there would be double the number of particles because dissociation takes place. As a result, the observed colligative property also becomes double than expected, and the molecular mass becomes half of the expected value. Here, the molecular mass of KCl, calculated by using the different colligative properties, is 37.5, which is half of the expected value, which is 74.5 grams. Now, similarly, in case of certain substances, association takes place in the solution, and this leads to the number of particles in the solution to decrease. This correspondingly results in the decrease in the value of the colligative properties. As colligative properties are inversely proportional to the molecular mass, therefore, higher value of molecular mass is obtained than the expected value. For this example, we see that ethanoic acid, when dissolved in benzene, undergoes dimerization, and here it shows a molecular mass of 120 grams instead of the expected 60 grams. Thus, when the molecular mass of a substance determined by studying any of the colligative properties come out to be different than the theoretically expected value, the substance is said to show abnormal molecular mass. Now, to calculate the extent of association or dissociation in a solution, Van Hoff introduced a factor I, called the Van Hoff factor. Now, this Van Hoff factor is defined as the ratio of the experimental value of the colligative property to the calculated value of the colligative property. Now, since the colligative property is inversely proportional to the molecular mass of the solute, the value of Van Hoff factor I can also be written as I is equal to the normal or calculated molecular mass divided by the abnormal or observed molecular mass, which can be written as MC by MO. For substances undergoing association or dissociation in the solution, the various expressions for the colligative properties are modified as follows. It should be noted here that if Van Hoff factor I is greater than 1, then there is dissociation of the solute in the solution, and if I is less than 1, the association of the solute in the solution takes place. Now, using Van Hoff factor, the extent of dissociation or association can be calculated. Now, when we talk about the degree of dissociation, the degree of dissociation is defined as the fraction of the total number of molecules or the total substance which undergoes dissociation to form the corresponding ions. Or in other words, the degree of dissociation, which is denoted by alpha, is equal to the number of molecules dissociated divided by the total number of molecules or moles that are taken. Now let AXBY be a weak electrolyte. Now when this electrolyte is dissolved in a solvent, it will undergo dissociation to form the corresponding ions, that is the corresponding anion and cation. Now if the concentration of the solute taken is 1 mole, or in other words, the initial concentration of the electrolyte before dissociation is 1 mole, and in this case it is obvious that before dissociation the concentration of the ions would be 0. So at equilibrium, if alpha is the degree of dissociation, now alpha in this case is the fraction of the solute or the electrolyte that has undergone dissociation, so the number of moles of the electrolyte that is left undissociated would be equal to 1 minus alpha, and the number of ions that are produced after dissociation would be equal to alpha into X and alpha into Y. So therefore the total number of moles after dissociation would be equal to 1 minus alpha plus alpha into X plus alpha into Y. Now let us consider, in this case X and Y are the number of cations and anions that are produced after dissociation. Now let us consider that the total number of ions, total number of positive and negative ions is equal to N. So we can write this relation as alpha into N, 1 minus alpha plus alpha into N, which can be simplified further as 1 plus N minus 1 into alpha. So this is the total number of moles of the solution after dissociation. Now when we talk about Van Hoff factor I, now Van Hoff factor I is the ratio of the observed colligative property to the theoretical value of the colligative property. So colligative property depends on the number of moles of the particles in the solution. So the observed colligative property will be equal to N1 plus N minus 1 into alpha, and the theoretical value of colligative property would be equal to 1. Now since we have taken 1 mole of A or 1 mole of the electrolyte before dissociation, so this implies that alpha is equal to I minus 1 divided by N minus 1. So this is called the degree of dissociation. Now in this case we know that I, or the Van Hoff factor, it is also equal to the calculated value of the molar mass divided by the observed value of the molar mass. Now here we know that since the solute undergoes dissociation, so therefore the observed molecular mass in this case will be lesser as compared to the calculated molecular mass. So here the value of I will be greater than 1. So in this case we know that the value of I will be greater than 1 since MO, or the observed molecular mass, will be less than the calculated molecular mass. Degree of association is the fraction of the total number of molecules which associate to form a bigger molecule. Degree of association is denoted by alpha, and it is equal to the number of molecules associated divided by the total number of moles of the solute taken. Now, if n moles of the solute A has undergone association to form n molecules. Now, if alpha is the degree of association and we start with 1 mole of A, that means the initial concentration of A before association would be equal to 1 mole. So at equilibrium, the concentration of A that is left unassociated or that did not undergo association will be equal to 1 minus alpha. Now, the initial concentration of the associated molecules will obviously be equal to 0, and at equilibrium, the concentration or the number of moles of the associated molecules will be equal to alpha divided by n. So therefore, the total number of moles after association is equal to 1 minus alpha divided plus alpha divided by n. Now, when we talk about Van Hoff factor, now Van Hoff factor is equal to the observed value of colligative property divided by the calculated value or the theoretical value of colligative property. So in this case, it would be equal to the observed value of colligative property is dependent on the number of moles in the solution. So it would be equal to 1 minus alpha plus alpha by n, and this will be equal to 1. Now, why 1? Because we have taken 1 mole of A before the association. So here, if you calculate the value of alpha, alpha will be equal to 1 minus I n divided by n minus 1. Now, this is the degree of association. Now, we also need to remember that since I is equal to the calculated value of molar mass divided by the observed value of molar mass, now here we know that since the solute undergoes association, so that means the observed value of molecular mass or molar mass will be greater than the calculated value of molar mass. So in this case, when a solute undergoes association, I will be less than 1 according to this relation.